Hello everyone. In this MATLAB and control systems tutorial, we explain how to define transfer functions and how to compute a Nyquist plot of a transfer function. Furthermore, we will explain how to extract vectors that define the Nyquist plot, such that you can perform some additional analysis. Okay, let's start. Let's start with the definition of transfer functions in MATLAB. And here, for simplicity, let's consider a second-order transfer function. Everything explained in this video tutorial can be generalized to higher-order transfer functions. The transfer function, in the general form of a second-order system, looks like this. In the numerator, we have the second-order polynomial with the general coefficients a2 multiplying s squared plus a1 multiplying s plus a0. Similarly, in the denominator, we have another polynomial that looks like this. b2 multiplying s squared plus b1 multiplying s plus b0. Over here, a2, a1, a0, b2, b1, and b0 are coefficients of corresponding polynomials. To define this transfer function in MATLAB, we need to define two arrays or two vectors. The first vector that I will denote by num will group, or it will collect, coefficients of the polynomial in the numerator. Consequently, the first vector will look like this. The second vector that I denoted by den, standing for denominator, will group the coefficients of the polynomial in the denominator. It will be b2, b1, and b0. After we define these two arrays or these two vectors, we can simply use the MATLAB function tf to define the transfer function. The first argument is numerator and the second argument is denominator. And this function will return a transfer function object. Okay, let's now explain how to do this in MATLAB. As an example, let's consider this transfer function. W is equal to s squared plus 0.1 s plus 0.2, and in the denominator we will have s squared plus 5s plus, for example, 0.1. Okay, let's define the transfer function. First of all, we need to define the numerator array. So we need to type numerator 1, 0.1, 0.2, 1, 0.1, 0.2. In the denominator, we have 1, 5, 0.1. And to define a transfer function, we'll use tf. We specify numerator and we specify denominator. And here's our transfer function. Before this, let me write clear such that I can clear my previous workspace, and let's evaluate this. Here's our transfer function. Let's compare the results. It's 1, 0.1, 0.2, 1, 5, 0.1. Perfect. Next, let's learn how to generate a Nyquist plot. We generate the Nyquist plot by using the function Nyquist. And as the argument of this function, we specify our transfer function. Let's evaluate this. And after some time, you will see the graph. So let me just bring up the graph for a second. Let me run this again with close all to close all the previous figures. And let me add here figure 1, just in case. Okay, here's our Nyquist plot. Now, if you click anywhere here, you can see the real, imaginary, and you can see the frequency at which this occurs. Okay, now you can shift this value and you can see how the real and imaginary values behave with respect to frequency. You can see basically the Nyquist plot. Okay. Next, if you do the right click on the Nyquist plot, you can see the characteristics. You can see the peak response. Here it is. Peak is given in decibel. It's basically gain at this frequency. Basically, it's at 0 frequency. Then you can see other things. You can see minimum stability margins. You can see the phase margin, delay margin at certain frequency. And you can see all the stability margins like this. You can also deselect this to only show the positive frequency. I always strongly suggest to everyone to only look at the positive frequency, since the Nyquist plot is symmetric with respect to the real axis. This is very important to keep in mind. Next, let's close this window. Now, in many applications, you would like to extract the numerical values of the Nyquist plot. That is, for certain frequencies, you will get the real and imaginary part. Let's learn how to do that in MATLAB. First, let us specify the frequency of interest. Over here, I will define a vector defining the frequency of interest. It will start from 0. It will have a step of 1, and let's go until, for example, 10,000. Okay. Once we define the frequency of interest, we can type Nyquist. And over here, we need to specify our system, and we need to specify as a second argument the frequency of interest. The output will actually be the real and imaginary parts. So I will type it like this. RP will stand for real part, and IP will start for the imaginary part. Okay, so let's execute this. And here it is. Now, what we actually extracted is real part and the imaginary part. Let's see what is RP. Here it is. Let's now do this. And you can see the real part, you can also see the imaginary part. Good. Next, let's create the vectors out of the real and imaginary parts, and let's plot them on the same graph. Let's see how to do that. Okay, first of all, let's define a for loop that goes from 1 until the length of frequency vector. And let's end that for loop. Over here, we will create another vector I'll call real part vector, and its ith entry will simply be extracted part of our RP. So it will be this. Similarly, we will define imaginary part vector. Its index I will be imaginary part, and then we'll have this thing, and again I. That's it. Let's run this. Okay, let's see the results. Here's our real part vector, and here's the imaginary part vector. Perfect. Now, what we can do, we can define another graph. I'll call it figure 2, and in this figure we can simply plot the real part as a function of frequency. So let's do that. Here it is. Now, over here you cannot see it very well, since the real part quickly converges to 1. Here it is. And here's this part of the from 0 to 5. So consequently, you would need to kind of increase the density of frequency to better see this part. Now, you can do the same thing for the imaginary part. You can simply type I pi p or pi vector, and you can define its own figure. Let's do that. Now here is not figure, here is simply plot. And here it is. Again, the frequency might be a little bit too coarse, and you would need to increase the frequency. Now, over here, you can actually plot on the same graph both real and imaginary parts. On the x-axis, or better to say, on the horizontal axis, you will plot real part vector, and on the imaginary axis you will plot the imaginary part vector. And that's it. Here it is. Perfect. Next, let's improve the density of these graphs by increasing, or better to say, by making the frequency to be more dense. So if we do this, if we just change this number, we will have a more denser frequency. Now we'll simply add semicolons over here and over here, and let's run everything again, and let's see the change. This will now take more time since the frequency is a little bit better. And you can see the graph. It looks a little bit better right now. Okay, that's all for today.